All right, ladies and gentlemen, today's class recording has started. So, on Friday, we started introducing this idea of, you might have put this here. We started talking about, like the name of this presentation said, how do we get these charges to do what we want them to do? We talked about charge and what charge was and how they apply forces to each other, but as we kind of talked about on Friday, our modern society is based on this idea of how do we get these charges to do what we want them to do. And so we started off talking about electric potential energy. Describe to me what is electrical potential energy. I know it says it up on the board, but what's your own version of it? So, all right, we can just read it up on the board.
It's a form of mechanical energy.
It's a form of mechanical energy too, but what does it depend on?
Position.
Position, but position in what?
Electric field.
An electric field, right? Whereas gravitational potential energy depends on position in a gravitational field, electric potential energy depends on position in an electric field. And we went through this demonstration here, right? And then the boxes showed up because it's like animation and stuff like that. But the first thing we did was we moved this proton from here to here. We moved positives closer to positives. That increased the electrical potential energy. But then when we let it go, it went back over here. So its potential energy decreased, but its kinetic energy increased. And we talked about the way that we could move this. I should probably just do this. I can actually like pull it up, right? So when we do this, right, that increased electrical potential energy, right? But that requires that we do what to that charge?
Work.
We have to do work to that charge in order to increase its electrical potential energy. If we let it go, this happens, right? And then the potential energy decreases, but kinetic energy increases. Although there is a way that we can move an object so its potential energy doesn't change, and that's perpendicular to the electric field. If we move it perpendicular to the electric field, nothing happens to its energy, right? All right, good there? So then on Friday at the end of class, we introduced a term that summarizes these ideas. What term sort of describes for us the electrical potential energy of an object or of a source? Voltage, right? Voltage always tells us about, where is it here? Voltage tells us about energy, and specifically about the changes in potential energy, right? And just real quick, right, to summarize, we said that if we have this charge and we move the charge within a battery, the battery does work on the charge to increase the electrical potential energy. But then, as that charge moves through the circuit, its potential energy is converted into other forms of energy. Sometimes it's kinetic energy from the movement of the charge. Sometimes that potential energy is converted into light and heat, depending on what's in our circuit. We talked about that, if it's a speaker, it could be converted into sound or something, right? But the biggest idea being that eventually, as these charges move through the circuit, any electrical potential energy that they gain from the battery is converted then back into other forms of energy as it travels through the circuit, okay? And different types of batteries will increase the energy more than other types of batteries. That's the voltage rating on the battery, right? But voltage always deals with energy, okay? Good there? All right. So now, today, right, we start introducing some other terms that, like I said, you may have heard of, but what do they actually mean? So the first one is current, all right? Current is defined as the rate at which electric charges pass through a certain area of a conductor. So if electric charges are moving, what kind of energy do they have? They have kinetic, right? This is one of that first step of turning electrical potential energy into other forms of energy. The first form we turn it into is kinetic, so the charges start moving. All right? Good there? So, Current is the movement of charge carriers. Technically, it could be the movement of a positive charge carrier or a negative charge carrier. But when we talk about where those charges come from, usually we see current as the flow of electrons, especially if we're talking about current flowing through a conductor where that conductor is metal. Usually current is the flow of electrons. Technically, it could also be positive charges, but usually it's the flow of electrons. Okay. What's going to cause these charges to move? Yes, we're converting electrical potential energy into kinetic, but that only happens because of a force. And that force is caused by a field. Current requires there to be an electric field that moves those charges. All right. Like I said, in a circuit, that battery provides the electric field that causes the charges to move. Charges won't go anywhere unless they interact with other charges, either like charges repelling or opposite charges attracting, but there has to be a force, and that force is caused by an electric field. So current only exists if there's an electric field to make it happen. All right? Good there? Okay. So some technical kind of stuff, but like we said, a lot of our discussion about voltage and current and resistance in this unit is more conceptual as opposed to calculations. But, right, current is measured in terms of delta Q over delta T. All right? Or we can just go Q over T. That's fine if the deltas confuse you. It's the same idea, right? We said that Q stands for what? We introduced Q a little bit earlier. Well, let's do T. That one's easier. What does T stand for? Time, right? If you look at your definition of current, right, what's the first two words that you wrote down? The rate. And we said rates always are measurement of something over time. Okay? It's the rate of what? Nope. What does it say in your definition that you wrote down?
Electric charges.
It's the rate of electric charges. Q stands for electric charge. Okay? We introduced that in one of our earlier outlines, okay? So you have charge per time, or coulomb per second, because coulomb is the unit for charge, second is the unit for time. When we have coulombs per second, we call that the ampere. An ampere is a derived unit, right, that combines two base units, okay? The rate of charge movement, the SI unit for current is the ampere. Oh, sorry. But if we think about our definition of charge, or sorry, if we think about our definition of current, the rate of charge movements, hopefully that makes sense. Okay? All right, good there? We okay with how we define currents? What we find is that there are two types of current. The first current is called direct current, and we use DC as the abbreviation for that. And like its name suggests, electrons only flow in one direction. All right? Most of our discussion of currents, especially in this unit, is going to focus on DC current because they're much easier to analyze than the other type of current, all right? So, DC currents are usually supplied by batteries, like in the example that we looked at on Friday, right? The battery does work on the charges and increases their potential energy. Then that causes the charge to move in one direction only, from the negative terminal of the battery to the positive terminal of the battery. Okay? A potential difference or a voltage source increases the electrical potential energy, which is then converted into other forms of energy, usually kinetic. All right? That's just sort of a summary of how we get current, right? Like we need something to increase the potential energy so that potential energy can turn into kinetic energy, and that's the movement part. Okay? The other form of current that we talk about is AC, alternating current. Okay? In the next part of this unit, after we hit the grading period break and we get into the next part, we'll talk about magnetism. We will find that there is a strong connection between electricity and magnetism. And so we can use magnetism to get current to happen. We refer to that as electromagnetism, all right? But when we use that, a lot of times we end up with charges flowing in two directions. Not simultaneously, but they change direction rapidly. They'll go this way for a little bit, then they'll turn around and go this way for a little bit, then they'll turn around and go this way for a little bit, then they'll turn around and go this way for a little bit. Doesn't seem really efficient, but as they're moving, that is current. Okay? So, and we'll talk way more about AC, like I said, in later parts of this chapter because it depends on our understanding of magnetism as well, but know that it exists. For the record, the electricity that comes out of the plug in the wall is AC. The electrons switch back and forth and back and forth and back and forth. They actually don't move very far at all, but it has to do with how we produce the current. And like I said, we'll talk way more about that later on. Okay? All right, so let's talk about these terms, current and voltage. Sometimes you'll see signs, right, that says high voltage or low, or what's really the dangerous thing? Well, we said voltage always relates to what? What does voltage describe for us? Potential energy, right? Voltage is always telling us about energy. Current is telling us what? What does current describe for us? The movement of charge, specifically how many charges are moving, right? So there's two things we have to look at here. Voltage tells us about the energy of each individual charge. Current tells us about how many charges are moving. So, if we have something that's low current and low voltage, what does that mean? We describe a situation as having low current and low voltage. What does that mean? Eric, go ahead. Low energy electrons. How many low energy electrons? Not very many low energy electrons, right? So in this case here, right, with low current and low voltage, right, each electron only carries a little bit of energy, and there aren't very many electrons. Is this a dangerous situation? Not really, right? This is, have you ever done a little experiment where you've taken a wire and you hold it to the two sides of a battery, and then you can you wrap the wire around a nail. Has anybody ever done this experiment before? You wrap the wire around a nail, and you hold the two sides to the two sides of a battery, and then you can use the nail like a magnet. You can pick up paper clips and stuff like that. That's low current, low voltage. All right. Not a lot of electrons. Each electron doesn't have a whole lot of energy. Really, not too dangerous of a situation. Okay. Good there? You'll see that we're going to follow quite a bit of a pattern here as we go along, right? So let's take a look at this situation. High current but low voltage. If we describe something as high current, low voltage, what is that telling us?
Low potential.
What does potential energy tell? What describes potential energy? Voltage. So if there's low voltage, does each charge have a lot of energy?
No.
Not really. But if there's high current, what does that mean? There's a lot of charges, right? So here, in a high current, low voltage situation, there's a lot. Each charge is only carrying a little bit of energy, but there are a lot of electrons. There are a lot of charge carriers. So, how much energy do we get? We can get a decent amount of energy, like it's described there as a moderate amount of energy. right? Granted, these are all relative terms, right? When we talk about little or many or moderate, right? These are all relative terms, they're all comparisons, okay? All right, good there? Low current, high voltage. What does this mean? We have something that's low current but high voltage. Not many charges, but each charge packs quite a punch, all right? So in this case here, each electron carries a lot of energy. That's the high voltage description, right? Remember, voltage tells us energy. But with low current, there just aren't very many charge carriers, all right? Best example of this right here, okay? Well, I mean, the best example, but a example of this would be something like a taser or a stun gun, okay? Tasers are very high voltage, like tens of thousands of volts, 10,000 volts, 15,000 volts. Just for perspective, the wall socket is 120 volts, all right? So a taser, each electron that comes out of a taser carries 10 times as much energy as each electron that comes out of the wall. But are there a lot of electrons? In the grand scheme of things, no, right? So a taser can do damage, but does it kill you like this socket will kill you? Could it? Sure, but we try to prevent that from happening, right? Because there just isn't that much current, right? So high voltage, low current, yeah, each electron packs a punch, but there aren't a whole lot of electrons there. So overall, the overall ability to do stuff, energy, is middle of the road, right? But then this is where things start getting really dangerous, right? High current, high voltage, right? What does it mean if we have something that's high current, high voltage?
A lot of energy.
A lot of energy per charge. And a lot of charges, right? When you go to, or when you see like those things in like the side of the road, like transformer stations or things like that, where you know things coming out of the power plant and it sends electricity to all the houses in the neighborhood, right? Yes, those are high voltage, but they're also high current, right? That's when it starts getting really dangerous, when we have high current and high voltage, all right? Because each charge carries a lot of energy, and there are a lot of charges. Now we can deliver a lot of energy, okay? All right, good there? In order for current to happen, what do we have to have? There's two things we have to have. You can look back in your notes if you want to, right? In order for current to happen, we have to have two things. Rate at which charge flows, that's like the definition of current. What did we say makes that happen? Got to have enough force in an electric field, right? So that's where the battery comes in. But just because we have a force doesn't necessarily mean electrons move. What else do we need to carry that electron from the high energy part of the battery to the low energy part of the battery? You got to have a conductor, all right? You have to have something for those charges to move through. So when we talk about those things, right, we talked about conductors and insulators, right? We talked about what makes something a good conductor, what makes something a good insulator. This is actually in your notes, it's sort of a bridge, okay? But we said that electrons, especially valence electrons, how tightly are we holding on to those individually as those atoms? If atoms hold on to their valence electrons very tightly, they're not good conductors, they're insulators. But metals usually don't hold on to their valence electrons very tightly, and so they're good conductors. How well something holds on to electrons or allows electrons to pass through it is measured by something that we call resistance. Okay? So, resistance, the impedance to charge flow through a material. The big fancy new word that you learned today, impedance, right? In unfancy words, how hard is it to make charges move through that material? The resistance is based on the type of atom that makes up that object, right? Generally speaking, nonmetals are going to have high resistance. They hold on to their valence electrons, so it's hard for charges to flow through them. Generally speaking, metals have low resistance because they don't hold on to their valence electrons, and charges flow through those materials pretty easy, right? Those are generalities, but that's usually what we end up with, all right? So, some materials allow charges to flow more easily than others based on those previously stated factors. Specifically, how tightly do those materials hold their valence electrons? Right? Where it says previously stated factors, right? Look, Chris made it. Wow. I'm giving. No, don't erase anything.
No.
You keep that right on there, right? So just. I'll point it out on the recording so you can go home.
Yeah.
If you want to, you can go home and show your mom this recording, all right? So
Yeah.
Chris jumped ahead, and he filled in letter C of his outline before I put this up on the board. Chris, what did you write in letter C of your outline?
How tightly electrons are held to individual atoms.
He wrote in how tightly electrons are held to individual atoms. That's a great thing to write in that space, all right? That's better than previously stated factors, because when you go back to look at your notes, you're not going to remember what the previously stated factors were, right? So, how tightly do those electrons hold on to individual atoms, all right? So, go home, show your mom this recording, and be like, Mom,
I'll make sure.
I got a shout out here on the recording. So. All right, good there? Figuring out the resistance of something depends on comparing two factors. And those two factors are voltage versus current. Okay? So if you go down to letter F down at the bottom, the resistance is a relationship between delta V, which is voltage, divided by the current, which is I. Right? So down there at the bottom, letter F in the outline, okay? Delta V over I, or if you want to actually write out voltage divided by current, you can do that too. Okay? That's how we measure the resistance of something. How much energy is it taking us to create current through this material? Okay? So, resistance is a relationship between the applied voltage and the resulting current. We measure resistance. Sorry, good. Still writing aloud. We measure resistance in a unit called the ohm. All right. The ohm is represented by the Greek letter omega. That's a capital omega. All right. Kind of looks like an upside down horseshoe. Okay. And ohm is a derived unit. That's a combination of some other units, right? It's 1 volt per amp. Because volt is how we measure voltage. Amp is how we measure current, right? So we look at the relationship there. The relationship between the voltage we apply, how much energy we're supplying, the current that results, and the resistance that is a result of that relationship between those three things, we refer to as Ohm's law. All right? So Ohm's law is basically just the equation for resistance, but we sort of rearrange it. V is equal to IR. All right? That's what goes in that space next to Ohm's law. All right? V is equal to IR. So when we look at Ohm's law, we're looking at the relationship between voltage, current, and resistance. Now, I threw this up here. Resistance is not dependent on the voltage. If you look at that relationship, you could mathematically make that statement that voltage and resistance are equally dependent, or sorry, directly related to one another because of where they are in that where they are in that equation. That's not really the case. It's just how it works out, sort of. All right. So over the next couple days, we're going to look at some circuits. We're going to look at some components, batteries, resistors, conductors, measurements of current, and how these three things are interrelated to one another. Okay? Don't worry about the factors that affect resistance, so you guys will not be responsible for that section right there. All right? And we'll go from there. All right? Good there? All right. Don't forget, you got a quiz that is due tomorrow. It's an online quiz. It's open note. Not over the voltage, current, and resistance stuff that we talked about. It's about charges that we talked about last week. Okay?